Good morning. Welcome to Rogni College of Engineering and Technology. I am Riji, Associate Professor, Department of ECE. Today we are going to discuss the topic uniformly spaced array with uniform excitation amplitude. In this, after completing this uniformly spaced array with uniform excitation, students will be able to define n element linear array and types of n element linear array. N element linear array, uniform amplitude and spacing. If the amplitude and spacing are both are uniform, the array is said to be n element linear array or uniform linear array. The array factor will be, array factor is equal to 1 e power j kd cos phi plus e power j 2 kd cos phi into e power j kd cos phi, whether the indication are given as the geometry and planar graph. N element linear array with uniform spacing can be given by the array factor, that is in terms of e power j n phi by 2 sine of n by 2 psi by sine n psi by 2. If the reference particle is the physical center of the array, then it can be written as array factor is equal to sine of n psi by 2 by sine psi by 2. So normalized significance of this n element linear array can be determined by sine of n by 2 psi by sine n psi by 2 with both null maximum value and minimum value. The normalized array factor can be determined using this graph. So when array factor is decreased, when you increase the angle of theta, the value of n will be getting decreased depend upon the length and size. You can see the plot, sine wave plot for different with respect to magnitude. So n element linear array will have 3 dB bandwidth and half power beamwidth symmetrical cases with both at the center. First side lobe level and second side lobe level can be easily determined for this array. A 3 element array of isotropic sources has the amplitude relationship. The spacing between the element is d psi by 2. Find the array factor and the first null. So you can see the broadside array. There are two classification with uniform amplitude, broadside array and end fire array. Based upon the length n equal to 10, and you can draw the broadside array with a different pattern. Grating lobe should avoid kd cos theta, 2n cos theta. So no grating lobe, directed d max will be 0. So null maximum half power beamwidth. For null theta and cos inverse plus or minus n by n lambda by 2. Maxima cos inverse m lambda by d. Half power point theta not equal to cos inverse 1.391 lambda by pi n d. Minor lobe cos inverse lambda by 2d 2s plus 1 by n. Beamwidth for uniform amplitude broadside array, first null bandwidth theta n equal to 2 into pi by 2 cos inverse lambda by d. Half power beamwidth theta n equal to 2 into pi by 2 minus cos inverse 1 by 391 lambda by pi n d. First side lobe theta is equal to 2 pi by 2 cos inverse 3 lambda by 2 n. So ordinary n fair array, that is parallel to the axis. So n equal to 10 and 4 equal to 6. You can see how the variation in the ordinary n fair array with this grating lobe. So if you take the value, the null will be cos inverse 1 minus lambda n lambda by n d, maximum cos inverse 1 minus m lambda by d. Half power point theta n equal to cos inverse 1 minus 1.391 lambda by pi d n. Minor lobe cos inverse 1 minus 2 d. So similar way you will get ordinary bandwidth for unequal amplitude. So for the phased scanning array, you will get the different value with respect to the kd cos pi. So both in valued for phased array as well as they given in terms of Hansen-Wood n fair array. So this Hansen-Wood n fair array can be determined by both the values. So Hansen-Wood n fair array will have the ordinary waveform as well as the physical waveform. So when we are drawing the pattern, we can see the variation both in this waves and this thing. So beamwidth for uniform amplitude will differ, and first null of bandwidth is also differ. So n element array have broadside array and n fair array. Based on this we can compute the value. Thank you.